Hello everyone, welcome back to the Game Engine Development Workshop series. Today we are going to finish up our script parser class. We just have one method to go here, and then start implementing our script stuff. And if we have time, we will actually start working on integrating our script into our engine. Because as we'll see, there's quite a lot of stuff to do in the script before we even get to the point where we can interact with our engine. And so I sort of separated those two out because they're both pretty big tasks. But let's get started here. The last one we have in the parser is just resolve int. And again, this is a bit of a weird method just because it's sort of left over from when I was, I talked about it last time, but when I was making sure that all of this could fit into 64-bit word instructions. And so I just took every value and turned it into an integer, even though right now it's basically just used as an int and a float. I don't know, there's probably a better way to do that if you keep this setup that we have now. But again, I sort of, when I started writing this, it was all designed to compile down or assemble down to machine code. And I sort of wanted to keep it that way just because I think it'll be a fun project for you to do as well. But anyways, let's get into it. So we sort of have the same conditions, or not conditions, but cases that we do with getArgType, where we take in a string and we have to classify it in some way. So getArgType, we have string literal, label, all this stuff. We'll have the same stuff down here in resolve int. So the first will be string literal. And we know this argument is a string literal if the first character is the string token. But if the last character is not the string token, then that's an error. This basically just means that string literals must be enclosed in double quotes, just the way that every language does it. And you can see here, and in other places in this sort of parser class, that we are enforcing a lot of, well, maybe not a lot, but we're enforcing some restrictions on the formatting of this code, even though they're not necessary. There's not really a reason to make it so that you can't have multiple labels on one line, or you can't have a label on the same line as an instruction. It's just that we're writing this, and so we can dictate that other than style, there's not really a reason to do that. You still have to do it. Same for string literals. All we really need to denote an argument as a string literal is one character, the first character being the string token. But we also enforce that the back character must be that, just because we want, because that makes sense. So at this point, we know it's a valid string literal, and we are going to write it into our script's memory, into RAM, and then return the pointer into RAM of the start of that string. Because this method, it takes in any arbitrary argument and returns some integer related to that argument that is then put into an args object. So we have this last string write field as well, which is the starting index of the last string written, and it starts at 4096, which is one past the end of RAM. But all we have to do is take the current value of it, subtract the length of the string we're trying to write, and then we have the starting location for that string. Now the reason that I've said length here is arg.size -1. So we know that our string is enclosed in double quotes, and we don't want to include those double quotes in the in the string. We don't want to store those. We only want to store what's between them. So that would be arg.size minus 2. But then also we have to account for the fact that these are just bytes, like contiguous bytes in memory. And so we have to like separate them from, we have to separate strings from each other with some character. And we're going to do that the same way C does it, and C++ do it, which is just sort of appending a 0 character, a null character on the end. And so we have arg.size minus 2 to chop off the quotation marks, but then plus 1 to account for the 0. So then we will go through each character. And write into memory. And I'll just have a ternary there. And that says if I'm at 1 minus the length of the string, so if this is the last character, I'll put in 0. Otherwise, I'll put in a character for my string, and I add 1 there, again, because I don't want to write in the starting quotation mark. And then once we've got that, we just return our last string write variable, because that is the start the byte in memory that our string starts at. And this Boolean here represents whether or not the value returned is actually a float, because I'm returning them all as ints, but for like float immediates, we need to know that the value should be read as a float. Okay, so that's string. Now we have special register. So we'll do the same thing as we did above. We'll just try and find it. And if it's in that map, we will return the index of it. Special registers is this map right here, so it has the name of the register to its index. So that's what it.second is. Second is the index, and that's going to be fed into get int register, or get in any of these 3 methods. It'll be the index field, and that'll resolve it to a pointer to the register itself. Then we have a regular register, which again we know if the first character is the sreg token. So all of our registers follow the form like $, character, and then a number. So the character is arg@1 and the number is arg@2, and then I just subtract the character 0 from that so that it's actually like the numeric value. And then we can just simply we can use this register offsets, this one right here, dot at group. So that gives us the index of the 0th of these registers. So T0 is 0, S0 is 8, so on. And then we just add in. Of course, that is not a float, so we also have false there. And at this point, we don't actually need to check that our string is long enough to do these operations, or that it's the correct length, which is 3, or that our register offsets map here contains it, because resolve int is called here, which is after get argtype, and get argtype makes sure that all of the format of any register is valid, and so if it's not valid, it'll yell at you. So we don't need to check that there. Next case is a float literal, which again, I'm just taking the lazy route of checking whether or not there's a period in the string. We can use the s2d method, which takes a string and converts it to a double. And then here I just pun that as an int64 and set the flag to true because this is a floating point value. And the last case is we have an integer. Now it can be useful in some cases, or just clearer, I guess, to write certain values in binary or hex, like if you're setting flags or whatever, or memory addresses. And so we can very easily include the option to write numbers in binary or hex. So if an int literal starts with 0x, then we will set the base equal to 16. If it's OB, we will set the base equal to 2. Otherwise, it's just 10 by default. And then we use this S2LL, S string to long, which is a 64-bit int. And I just sort of have this other ugly conditional here, which is if base is not equal 10, which means that there are two characters preceding the actual value we want to parse, so OX or OB. Then we'll pass in arg.substring from 2. So we'll just get rid of the OX or the OB. Otherwise, we just leave it on there. All right. Okay. So that is our script parser. Before we go on, I'll just make sure that this all compiles. Probably mess something up somewhere. Unresolved external script. Okay, yeah, so that's just complaining about these. Okay, so we'll see this in a bit. As we get a little bit into our script, we can actually start writing some scripts and making use of this class. So create a new file, script.cpp. Take all of these and this one. Oh. And that one. Okay, so here we'll just set a bunch of default values. Oh, did I forget? Oh. Got the file path. Okay, so we have at the bottom here all of these, well, this array and then these two maps. And we need to initialize these from the values contained within this single vector. And again, this is just a convenience thing so that we can put all the information we need in this vector, so just so we have to write it once and then use the constructor to initialize all of these for us. So we'll just check if one of them is empty. And if it is, then we will go through our vector. Okay, so we get the current instruction, which has name, description, and an op. And then command names, maps, uints, so opcodes to the name of a command. The uint will just be, it's like the index, and for this we don't really care because we're not we're not turning these instructions into 64-bit words, so we don't really care. But so I'll just use the index that they are at in the vector. But if you were doing that, you might want to like hard code those yourselves. A description is just a string to a command description. So the name command description is the opcode, and then the list of arguments. And then s_operations.i is cur.up. So that's just the list of function pointers. And that's what operation is here. It's just like a type def function pointer. Okay. So that'll happen once, just statically. We'll just initialize all of these static structures. And then we will make a script parser with the given file path, passing it ourselves, and call parse on it, and set in compiled equal to that, because that's just going to return whether or not there was an error. And we want to know whether or not we compiled, because if you run the script and it failed to compile, that doesn't make any sense. So we need to prevent that. Okay. Now we have run, which is pretty simple. So this is going to be called, this is like, I'm passing in a runtime, which is just a render in a world. I'm calling it from this host. So the host object is this thing, and then here's all the environment. And here we'll check if we even compiled. I think I'll go ahead and implement this just so I don't forget. Okay, so we have these instructions: sleep and block. So sleep takes in an int register or an int immediate, so does block. And sleep pauses the current script's execution, just this one script, for the given number of milliseconds. And it will resume when it's done sleeping. It'll just continue going from where it left off. Block sort of has the same properties, except that it blocks all execution, not just this script, like the execution of the whole engine, the whole program, everything. And that's not terribly useful. I just included it because why not? And so sleep end will be set by the sleep instruction. It'll take the current time of the render and add whatever argument it was given to that, and that'll calculate sleep end. So if we try to run before we're done sleeping, just return 0, like we're not going to run. If we aren't sleeping, then program counter, we should start back at our entry point. And then we set sleeping equal to false after that. And that's important because if we set, because like once we've done this, we know we're not sleeping. So we could do that. But that would make it so that when we're done sleeping, we always resume from the entry point, which is not quite what we want. We want to resume from the point where we started sleeping. But then every other time, like if execution ends normally, we just want to start from the entry point. Okay, so then we'll reset our special registers. So our host will be host index, just that special value that says operate on the host, which is -1. object count will be the number of scriptables in our environment array here, our environment list. And we'll just reset flags to 0. And then reset spawn queue, which I'll talk. I don't know, we might not get to that today, but that's like the very end. Okay, so while we aren't aborting and there are still instructions left to run, we will get the next instruction. And do this super weird syntax. Okay, so the current instruction is from im instructions, which is a vector of args. Args contain the opcode, so the index into this array of function pointers. So we get the function pointer at that index, and then like invoke it on the current object, on this, and then pass in these things. And those things are in this order defined here in this macro, which just because this is the macro we're going to use, this is the order we have to put them in here. So the args themselves, that should be args, the current time, the delta time of the current frame, world, the host, and the environment. And then once we're all done, our return value will be the flags register. Okay, pretty simple. Then we have these get register things, which are also quite simple. So these have to line up with the values returned by resolve int. Because this is the function where we actually take a string, so a string like a register string, and return some integer. And so for the special registers, that's right here. But for these, we just get the base address of that group, or the base index of that group of registers, and then just add whatever the number is to it. So like T3 would be base index is 0 plus 3. There you go. So we just need to make sure that those line up. And going back to the spec here, we have registers. So this details like what the types of all the registers are. So the int registers are the T, A0 to A2, R0 to R2, the S, and then all the special ones. So T and S are all int, and then A0 to 2 are all int. So anything less than or equal to 18 will give us a register in that range. The R registers, so R0 to R2. R starts at 24, so that's R0, and then R2 will be 26. And then we have the special. So special registers, the index starts at 49. So if we're greater than or equal to 49, otherwise we will return null pointer. And the reason I do these minuses here is because these are all indexes into the array of int registers, which are just like contiguous. So like the int register at 49 doesn't exist. And so these first 18 line up, but then we need to go from 24, that needs to turn into 19. And then so on. That's why I have those weird subtractions in there. I don't like magic numbers, but I don't really see a need to define constants for those. Okay, so float registers, we have sort of the same thing. You could look at this, but I just have it over here. So that's the A. Then we'll do R. And then the F registers. We have the vector, go from 22 to 23, 30 to 31, and 40 to 48 for the V registers. Okay. Then we just have another utility function. This will just be used when like accessing memory to make sure we've been given a valid pointer. Okay, so let's start off by writing the like most basic instructions that we can so that we actually see something. So we'll start off with these debug guys, which just print a value. So we have debug for ints, debug f for floats, vector, and then strings. And I'll use my macro there so I don't have to just copy paste that function signature every time. Okay. So that has, I just like print out the file path. That probably won't be sufficient for any like game of scale, because you might have multiple things. You probably will have multiple things that use the same scripts. So it would be best to assign like some unique ID to each script that is then like otherwise available to the user of your engine so that they know. I'm not sure, but that could get confusing. But for us, it's fine. Then I'll write this other macro, ROI. That's sort of a dumb name, but all it does is take two things. The first thing must be a register, like a register pointer. And if that pointer is not null pointer, it'll return the value in that register. Otherwise, it'll return whatever expression you give it. So initially this stood for register or immediate, but then I realized you could just sort of chain them together, and so I'll often put another call to ROI in this I position there. But this just says that if I have been given an integer register as my argument, dereference that and print that value. Otherwise, print the immediate value. And the reason I do that is because debug takes either an int register or an immediate value. So we need to account for both. I'll just copy paste this. So we have debug, debug f, debug v, and debug s. So debug F will be much the same, just with the float register and the float immediate instead. And then debug V, this one doesn't actually, this one only takes a vector register. There's no such thing as a vector immediate, because that would be 2 values. So we don't need that anymore. We can just go straight to args.v at 0. Like that. And then debug S, this one is pretty cool. So this one just takes an integer, an immediate, or an immediate string. And immediate strings, if you remember in our script parser here, in resolve int, they are put into memory for us automatically, and then we just return the index at which they start. So really, when I pass something to debug string, I'm not passing a string, I'm passing a pointer into memory. And so that doesn't have to be something like auto-generated by the compiler here. It can also just be a value in a register or a hard-coded immediate value. All I'm doing is taking whatever value I've got and then reading from memory at that index. Okay. And I just cast that to a char, which means that in memory is like the base sort of address, and then I add on whatever integer value I've been given, and I read that as a char pointer, which will, by default, because printf uses like the C string convention, just read until it hits a 0 character, which is the same way we've stored them over here. Okay, so once we've got that going, go ahead and undefine that macro again, just in case. We can create some entries for those in our instructions vector here. Okay, so we have debug F, V, and S. Just make sure that all of my argument types line up the spec. So I have IMI, FMF, V, and IMI-MS. Good. So register, immediate, register, immediate, register, register, or immediate. Okay, and then all the values in here will automatically, in our constructor, be used to populate these structures here into all the necessary formats. Now if I compile this, I'm surprised that worked. I kind of don't trust that. Let's try including script, and we can just write a simple example. Okay, so I'll make a new folder in the resource folder to hold all of our scripts. Make a new file called test.script. And then in here, we can just do like debug s hello world. Okay, let's try compiling again because I don't believe that I didn't make any mistakes. Wow, really? Okay. Huh. My lucky day. Okay, so we've got something. It seems we've made a very simple error. I believe we're just not incrementing the program counter. Yeah, so as part of this like run loop here, after we run each instruction, obviously we want to go on to the next instruction. So now if we do this guy, we just get that once. Excellent. Very easy. Now, I mean, I could like do some more with this. Like I could do the other debug methods. They won't be very interesting though. Like I can debug on a register, and that it'll just print 0 because everything's initialized. We don't actually have any instructions to put stuff into memory yet. The only way we can do that is through like the script parser's automated way of doing it for strings. So that should be our next task, is actually moving around some memory so that we can print it out and see it. So let's do like, there's an example in here somewhere of the stack. Yeah, there we go. Let's just do enough so that we can do this simple example here. So we need move low, move high, push and pop. So push and pop are the stack instructions. Let me just sort of section these off, because this will get crazy eventually. Okay, so we have push, pop, move low, move high. So push, let's see what this guy takes. Where is it? Here we go. Takes any register, I, F, or V. And same for pop. So we actually just need to check like which kind of register we've been given. I guess you could do another macro for this, but it's an uncommon operation. We don't want to dereference that. We just want to check whether or not it's null pointer. And then we push that dereferenced. Now the reason we can't do stack push on like an ROI statement with all 3 of our registers there, like I'll just show you what I mean. So if the int one exists, use it. Otherwise, if the float one exists, use it. Otherwise, use that. And I don't think that'll work because this has like different types. Because we have an int pointer, a float pointer, and a vector pointer. But maybe it will work. I don't know. Maybe it was only popping that was weird. So I'll sort of leave that commented out. Then we'll do it the crude way at first. Okay, so that's push, and pop will be similar to this. And this one we do actually have to write them as separate statements because they take different, we want to use different template arguments here. Because stack pop takes in a type named t and returns that t. Because remember, the stack is like typeless, it just stores bits, and all the casting and stuff has to be done when you get a value from the stack. So that's what this does. Okay, then we have move low and move high. Now so move low will take a value and erase whatever value is in whatever bits are in the lower 32 bits of the register and replace them with this value. and move high will do the opposite. It'll do that for the upper 32 bits. And the reason these exist, they don't need to exist right now, just because like the way we're storing immediate values is just straight up int64. But when you are cramming everything into 64-bit words, obviously you can't use 64 bits for your immediates, and so like if you want to access like the top half of a register, you basically have to have a dedicated instruction for that. And again, that's not necessary right now, but I just thought I would include that in this example because it's an interesting problem that you will very, very quickly run into if you do try to you know, okay, so we just AND this value with the high mask, which is in here, the high mask being all ones for the upper 32 and all zeros for the lower 32. So this basically means keep the upper half and then replace the lower half with this new value. And then move high will be the opposite. We'll just AND with sreg mask low, and then we will take the value we're given here and shift it left by 32. Okay, that looks good. Let's now add them down here. Have push, pop, move low, and move high. What do these take? Probably, yeah, IMI. Okay, let's try compiling that. All right. And then we can try out this example we have here. Where to go? There it is. Okay, so we've got some magic numbers here. So T0 is always going to be initialized to 0. So move low this magic number into T0, and then that was it. And then move high this other magic number into T0. So this sets the lower 32 bits of this to be that, and the upper 32 to be that. And we will push T0 onto the stack, pop it off into F0, and then print out F0. Let's see what we get. Ah, interesting. Instruction move L expects 1 arguments, but 2 were given. So we can see here that our error reporting system works nicely, because we have the file path, colon, and then the line number. So line number 1, which is good. And then the instruction is printed correctly, expects 1 arguments, but 2 were given. And then the script doesn't even run. So I think I just messed up the, I think I just gave him 1. Yeah, so IMI and then I, of course. So the sort of convention I followed for like memory instructions is that you have the left-hand argument is like move from, and the right-hand argument is move to. So in this case, we move from another register or just a constant value, and then move it to this other register on the right. Now if we run that, this should work. Oh. Aha. Interesting. So what do we got here? We have args.v is null pointer, and it's trying to dereference that for some reason. Very interesting. So it would seem, so that was in what? That was in pop. It seems like because that would only happen. This is only dereferenced if neither of these are true. This shouldn't be true, but this should be, because the register we're giving is F0. So that might mean that something in our resolve int went wrong. In our reg token. Either that or maybe not that. It might also be in get float register. Let's double check those numbers. 19 and 21, 27, 29, 32, 39. Oh, okay. Let's just print out the index we're getting. Looks like it is in the resolve int function there. We're getting 40. Yeah. Interesting. F0 is 40 for some reason. Oh wait, that's right. Let's double check this. That is right, but it should not be right. It certainly should not be right. Oh, I gotta scroll up in my notes a ways. That was a ways back. Ah, this should be F, and that should be V. That was a dumb mistake. Float starts at 32, V starts at 40. Probably pretty obvious to you. Now if we run, we should get this, and we get this nice little number there. So again, that's the result of like loading in some values to an int register, pushing those bits onto the stack, and then popping those bits off into a float register, and then printing that as a float. You can see if we print that value just as it's the int register that it is. I wish it would stop doing that. Just print that value as an int register. It's some number that's not nearly as funny. But that's just a dumb example. Okay, so we've got a point now, gotten to a point now where we can move some stuff around in memory and print it out so we can see what's going on. At this point, there's not really like, until we get to the end of writing all these instructions, to where like these last couple are like actually interacting with the engine, there's not too much incentive to go in any order. I just sort of did debug first so we could see something, and then basic moving around so we could see more stuff. But at this point, like I think I'm just going to go down the list and just do them in order. There's quite a bit of boilerplate at the beginning here, obviously, because we have all these math functions for the 3 different types. Yeah, let's get going. So we have add. I don't know, I really wish the formatter wouldn't do that to me, but whatever. So we have add f, add v, have sub f and sub v, and mul f and v, and then div f and v. Okay. So these also, like, it's probably not necessary to have separate ones for each like type of register. The reason I do, though, is because, well, two reasons. One, I think it's nice to have each instruction be like perfectly explicit about what it does, because these are supposed to be like atoms, basically. They're like the fundamental units of any programming, of any like computer operations, and so they should do one thing and be very clear about what that one thing is. And so it's nice to know when I call add that it's only going to store something in an int register, and I can't pass it in like any type of register, which you might be able to. I think that would be a bit messier. Again, it would like make the implementation a bit messier, and it would also make it less clear what's going on. And then I believe you also run into some issues of casting. Like if my add method if my add method can store something in an int register, a float register, or a vec register, it becomes again very ugly to like figure out which one to put it in and how to cast it, how to determine the other two arguments as well. And I don't know. So I've sort of just gone the lazy route of copy paste a bunch. So add v is actually a bit special in that it takes as its second argument a float vec register or a float immediate, in which case it'll just apply, well, in these two cases, it'll just apply the float to both of its values, to x and y. We have that sort of nested macro there. Okay, and then I think I shouldn't have written all those out beforehand. That was a waste of time. Now it's much easier to just do that. Because now I just rename these and then change all the symbols. Okay. All right. And we can see here the same sort of convention that I said, where like the whatever register is being written to is the rightmost argument. So in this case, args.i at 2 is the result register, and the ones to the left of that, 0 and 1, are the source registers. And another thing that I didn't really explain, I don't think, about the way that our like create method here works in the parser is when we have this case, we have two cases. One is the argument is an immediate value, otherwise it's a register. And if it's a register, we just write into like the index of the register we set is the index of the argument. So if this register is given as the leftmost argument, it'll be 0. If it's the middle one, it'll be 1, and if it's the right one, it'll be 2. So we do it that way instead of like filling those arrays from left to right. So like saying if my I don't know, if I had a register as my second argument, like the middle one, that will always be written into the first slot of this, never the 0th slot. And that consistency is necessary, I think. Otherwise, you'd have to. I don't even know how you do it, but basically, it just makes these cases where some of these instructions take either a register or an immediate. It just makes it so that regardless of whether or not they have a register, any following arguments will always be in the same place. Okay, so now we can just add those guys. So we have add and that takes what am I? Probably not, right? Yeah, that still just takes the left-hand one must be an immediate, and the middle one, no, the left-hand one must be a register, and the middle one can be an immediate. And that's a pattern that I stick to a lot as well. Even though, you know, at this point, we do have full capacity to store two 64-bit immediate values. You wouldn't normally, and so I had very limited support for like two immediate values in a single instruction, if any. And so only one of the arguments is allowed to be an immediate. But if you're not interested in like actually writing a proper instruction set for all this, then you don't need to worry about that. You could just say, hey, this can also be an immediate, and then you can add two constants if you'd ever want to do that. I don't know why you would, but you could do that and it would all just work. We have add v, which is a bit more complicated. I think it has some weird arguments. Yeah, fv mf. Now this you could also throw on an either, because like the way this is implemented, it's just addition. So we have, a vector object plus something else, and that plus works for like either a vector or just a value. See, we have just a value or a vector of values. But I think the reason I don't have it as accepting an integer is because vectors themselves store floats, and so that would be sort of implicit casting, which again I want to avoid. We have the sub. I think these all take the same types of arguments. Yeah, it looks like they do. Okay, so now we should be able to like do math on some registers. So just to test this out, we can just use these move low and move high that we've got. So I could say move low, I don't know, 5 into T0, and move 10 into T1. Then add those, and just print them all out. See what we get. So T0 has 5, T1 has 10, and T2 has the sum of those 15. And we could multiply them as well if we want 50. Pretty cool. But at this point, we can't like move stuff into float registers or vec registers, so we're still kind of limited in what we can do. Another thing I should mention is this, like you can see this is syntax highlighted. I actually wrote a Visual Studio extension that I can I think I just set up like a download link for it on my website that you can get if you want. I don't know how to do the same thing for Xcode. I don't know if it's possible. But sorry, I use Visual Studio, and this was sort of a pain to set up. But it is useful. I don't. It. I might. I probably want to update it before I distribute it, just because I don't think it's actually completely finished yet. The project for it actually is right here. Like by accident, I put it in this folder. So I don't think it has support for all of the commands. Like there's none of the. I don't know. It has the object commands. It just doesn't have like spawn and time and stuff. So I'll go through that and make sure it's all cleaned up, and then I can just put it on my website, and I'll put a download link in the description. And it'll be like a actually, I'm not sure what it be, because when it compiles, it builds as like these three things. I'm not sure how many of those are necessary. So I think I'll just zip these up into a folder. But to install it, you just double click on this .vsix, and you have to like close Visual Studio down. But then the next time you bring it up, it'll have all the syntax highlighting. So it's pretty good. It's not perfect though. Like, and I don't know if this is something I can change in the extension or a Visual Studio setting itself. But like, it tries to like it does this, where it has like an autocomplete thing, and then I just want to hit tab to like tab over, but it selects that. So I don't know. Again, I don't know if that's an extension thing or what, but for the most part, it's pretty good. And this is just like, even this is way better than just the basic white text that we would get otherwise, like we do for GLSL. But anyways, back to this script. So I think that's all. Yeah, that's all the basic math stuff. Now we can do the bitwise math. So we have and this actually, something I learned while writing these is that C++ supports like the stupid, ridiculous, like Python style words as operators thing, where instead of doing double ampersand, you can write the word and it has the same thing. Same for like all of these operators. So we can't actually name them that because that's an operator name. So I just throw a B on the front, bitwise and. I hate that though. I don't know. Everything about Python just makes me mad, really. Okay, so we have and, XOR, or not, and then shift left and right. So and XOR, or not just takes one thing. Or sorry, that's not just takes two arguments. And actually the first one can be an immediate as well. Then we have shift left and shift right. And just to be safe, I like to do this because I'm pretty sure it's fine to leave no parentheses, but I know that this has very low precedence, and that can trip you up, not trick you up. Okay, so that's all the bitwise stuff. Even though we had to name these functions like stupidly, we can still, like, we don't have to name them like that for the user, because the user just sees a string, right? And that's their instruction, but under the hood, it can be whatever it has to be. We have and, XOR, or, not, and the shifts. So again, I'll name these normally. And over here, I have to do the stupid names. Okay, and these will only take integers because it doesn't make sense really to do bitwise stuff on a float. And even if you wanted to, for whatever reason, you can just push a float to the stack, pop it into an int register, and then do it like that. So we'll only accept integer stuff here. Looks like they all take oh, those are out of line. All take an I as the first one, except for not, which also takes mi. But I'll actually leave it like that just so I can do this. Okay, but not takes, I think just get rid of that, right? Yeah, that looks good. Okay. So we can test this real quick. Let's say I want to move, I'll do a binary number into T0. Then I'll take the AND of T0 and like that into T1 and an XOR of, XOR doesn't, well, okay, so what should we expect here? So we have AND of that and that, so that should be this, which is 16. So that first line should be 16, and then T3 should be the XOR of this and that, which should just give us 4, because that's the only one that's different. So we should get 16 and 4. Right, seems to work well enough. And we also just tested there that we can write numbers in binary, which is nice. Okay, now we just have a bunch of like boring math functions. I'll start with the trig. And again, these I have to name sort of differently because the like C math or one of those includes like defines all of these things not in a namespace, which is lovely. So I have to name them slightly differently. And these are only going to take floats, I think. Yeah, I mean, they could take ints, but they should always write to a float. Only really makes sense for them to do floats as well, so I don't know. But again, something you can change if you want. Sine, cosine, tan, sine a cos a tan. And then a tan, of course, actually takes 2 arguments, like that. And I forget whether those are in radians or degrees. Probably radians. Okay, so sine, cosine. Then the inverses. And those all just take floats all the way through. Okay, And we can test. Oh no, we actually can't test this out because we can't move stuff into float registers yet. But that's fine. There's no need to test those. I'm sure you can tell what they do. And they're so simple that like we don't need to prove that they work. Okay, next we'll just have some other math functions that don't fit into any category really. We'll have min, max, for int, float, and vec. Then we'll have power, square root, absolute values for all three, and then random numbers. Again, I have to name some of these a bit weird because abs you can see is already defined by, here we go, standard lib.h, old C header, before namespaces existed. Okay, so this one will be for integers. And the first argument will always be a register. The second can be a register or an immediate. We just have max right there. And actually, I'll copy these because they're the exact same for float. The only difference being these other registers. Okay, and then for vector, I decided to have it only take in one vector instead of two because it doesn't, like, it's just sort of arbitrary to say that one vector is greater than another. Like how do you determine greater? And so what this will do is just return the minimum of x and y of a single vector, like the minimum component of a vector, and store it in a float register. And then the other, same thing there, but max. Okay, power will return, put into a float register. So this only allows you to use an immediate as the power, like the exponent, not as the base. So I mean, you could define like another instruction that lets you use an immediate as the base, but I figured that would be way more like uncommon, so I didn't really see a need to do that. And square root will be very, very similar. And for this one, I think I'll also allow, oh, that should be 2. That should not be, that should be 1. For this one, I will allow immediates as well, even though like the square root of an immediate, you can just calculate that and hard code it yourself. But it's kind of messy. It's a lot cleaner to read it, to write code where you can just, do that. Say like square root of 2 instead of 1.4, 1, whatever. Okay, absolute. Another one where we have a separate instruction for all 3 types. And then for vector, we can actually just use the abs method on the vector. And then random, so these will take in, like 2 arguments that are a range for the random, and then it'll put some random number in that range into the 3rd argument, which will be a register. We have 1 for ints and then 1 for floats. Like that. Copy that. Just replace all that. And we've used some functions here that we don't actually have. So let's just define those quickly in our math file. We have pow, and then rand. I'll just copy that because I can't type. So standard rand is a bit weird in that it returns like some value between 0 and rand max, which I don't know what it is. Like, what is that, 65535 or 32768 something? I don't know. I think the maximum like 16-bit signed value of an integer. I don't know why it's like that. That's probably just a legacy thing. But we want to take whatever value it gives us and divide by the max to sort of normalize it into 0 and 1. And then once we've done that, we can just put it in the range that we've given. So max is excluded, but min is included. Max minus min plus min. Okay. And then just a couple more functions here. Sign. Return the sign of an int, a float, and a vector. Sign meaning do we? I don't even know if we have this actually. Let's see. Oh yeah, I think we do. Yeah, we do. So sign meaning if it's 0, the sign is 0. If it's greater than 1, it's 1. If it's negative, it's negative 1. That's all sign is. And that can be useful sometimes, so might as well add it. Okay, so I'll go ahead and add all of these guys. This is going to take a while. You know, I think I have this open in another tab. I'll just copy those because I don't want to make you watch me type all these, and I don't want to type all them either. And plus, you have access to this guy, so you can just see all the variable types they take anyways. Okay, but I will just compile to make sure it all works at least. All right. Next we have even more math functions, just a couple left for the vector. So we've got dot for dot product. And we have magnitude of a vector, angle of a vector, angle between two vectors, and a normal. I couldn't think of a better name to distinguish these two. Then this one is just the angle of a single vector, and this is ang_v, angle vectors, the angle between two. And then get the normalized vector. Okay, so we can add those, and same thing, I'll just copy those over because no need to make you watch me do those. I think we'll do memory next and then call it for now. Finish the rest next time. So we already have a few in memory, but we can go ahead and add some more. So I'll add just a basic move for an int register. And as you can see, this takes two arguments. The right argument is the destination, and the left argument is either a float register, an int register, or an int immediate. And this will do some casting. And this, I think, I mean, clearly it violates like what I said about how casting is like sort of hidden behavior and can be confusing. But in this case, I don't think it's terrible. I guess you could, like, the reason it's here is because this is the only way to move values between these two types of registers, float and int. Like, you need a way to do that, and you could create a separate instruction explicitly for that. But I don't know, it's like simple enough that I don't think it's that much of a foul. I'll just copy this. We have the same thing for float. Move F. Except this time using the float immediate. We have move V. Which is a bit of a weird one. It has sort of like a non-standard argument pattern, I would say. Where is it? Oh, it's not on here. Wow, the spec is incomplete. Well, let me add that. Move V. We'll take that, one of these, some register or float immediate, and just move them into the whole vector. So obviously if we have a vector, then we want to copy element-wise. Otherwise, we want to copy one by one. Like no, that's not right. We want to copy whichever of these single values into both of the values of the vector. So if we give a float register, we want that to be used for both x and y of the resulting register. So I think we can just do args.v at 1 equals let's see, it takes args.that or an int or a float or a float immediate. Will that work? I think this will work. Compile and see. Yeah. And the reason this works is because we have we have this constructor, which takes, well, we have both this constructor and this copy constructor. So copy takes a vector and like just copies both the values, but this one takes a single value and assigns both those values to both of these fields. So I think, yeah, that should do that, where if it resolves to this, it'll copy it as a vector using the copy constructor, otherwise it'll do the single element constructor. I want to actually test that though, but I'll get to that in a minute. So move x is just going to be, well, basically the same thing that we have here, kind of. We're just going to, instead of moving a value into both the x and y, we're just going to move it into the x. So args.v at 1.x, and I think I'll have to rearrange this slightly. Ooh, this is tricky. I'll just do like a dumb if statement. So if my argument, my left-hand argument is a register, or is a vector register, I'll do that. Otherwise, I'll get whatever that value is. There's probably some way to do that in a single line though. And then move y will be the same thing, just setting the y value instead. Okay. Only two we have left to do for memory is storing to RAM and loading from RAM. And these are kind of big ones, so good to end on. We'll get the index and then check that it's valid. Okay. Now, we've got to do something pretty tragic here with that pointer. So memory is like bytes. It's just chars. It's 8-bit, like a sequence of 8-bit values. But we want to write to it 8 bytes at a time, because all the stuff we're going to be storing are 8 bytes long. 64-bit ints, doubles, which are 64 bits, and then vec2s, which are two 32-bit floats, so 64. And so we get this pointer, the pointer into memory at the index we want, cast it, which is a uchar pointer, cast it into a ulong pointer, and then dereference that so that we get so that we write 8 bytes basically. Because if we just dereference the uchar, it'll only write a uchar's worth, but if we dereference ulong, it'll write 8. And then we take whatever register value we've been given and pun that as a ulong and just write it in, and that should work. Next we have load from memory. Which, same thing, we're going to get the index, check that. And then write, so this one we will actually need an if statement, again, because we have to cast to different things. Because you can't like assign a vector value to like an int register. So we got to check which one we were given. have int, float, and vec. Okay. Let's add the descriptions for each of those. I'll just copy them over. Okay, so which one did I want to try out? I wanted to try out, well, I want to try out these two. Those are pretty cool. But also my move V. Okay, so let's do a move V on a float immediate of 5 into V0, and then print it out. That should give us 5 in both. And then I want to store that at, I'll just say index 0. And again, here we have the convention of like store from and to. In this case, 2 is just an index in the memory. And then I will load from index 0 in memory into v1 and print that out. And we should get the same thing. Right. And it requires L value. Oh, yeah, I can't pun that. That's right, because that's an R value, but I can certainly cast it. Not convert from vec2 to ulong. Oh. Yeah, I think this is going to have to be an if statement as well. I mean, I could define another macro, but I forgot that this one just dereferences those pointers. So yeah, I'll just do it as an ugly like if chain like this. I, F, and V. Okay. Okay, so we don't quite get what I was hoping for. Unfortunate. I did see some type of warning here. Version. Da 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 da. Oh, I need to actually cast that. I'm not sure what it's complaining about here. Conversion from scriptfp to T. Oh, not scriptfp. Scriptfp is a double. My vector stores floats. Lovely. That's awesome. All these operators make sure that whatever type of vector we have, we're taking in arguments of the same type so that weird stuff like that doesn't slip through the cracks. And when you are, counting bits essentially with the stuff this low level, it's very important that you get all this right. Okay, so why is this not working? I'm storing it at 0. I'm loading it. I am not sure. Oh, that's probably why, because I just copied that and forgot to change the order. No, those should also be 0. Okay, now we should get something that works. Fingers crossed. Perfect. So we store, we load 5 into both v0, we store that at location 0, and then we read from location 0. Now, just to do something a bit cool, get a bit wacky here, we can offset that by 4 and read 5-0. So I'll just do a short paint demonstration and then wrap it up because I think once again I'm over time. I am. So we have like 8 bytes in memory, and we have a vector v0 that is 5 and 5. So what happens is, I don't know how to draw this best, but like 5 gets written into these 4 bytes, as well as these 4 bytes, because this stores floats, and a float is 4 bytes, but our load instruction, or sorry, store instruction, does it as a ulong, which is 8 bytes. So we write this thing, these 2 4 bytes, as a single 8-byte group into this, and that'll be something. I don't know what value that'll be. But then, like just below this, we have another block, which is, same thing, 8 bytes. Each of these rows, I guess you could think of as a ulong in our memory. And this, it's all 0 initialized. So this has 0 there and there, and there and there. And so we write v0 in starting here, because we write it at 0. But then if we read from here, what do we get? We get 5, and then we wrap back around down to here, and 0. So you can sort of offset it like that, which, I don't know, probably not useful, but it's a cool demonstration of how that works. Okay, so yeah, we'll leave that there, and when we come back next time, we will wrap up sort of the basic instruction set with control functions, so branching, calling, returning, jumping, and then after that, we will start integrating with our engine, which is the fun part, the cool part. So I'll see you then.